artificial intelligence is running out of human data. To reach superintelligence, artificial intelligence must create its own synthetic data. Chapter 1. The Data Wall and Scarcity. For over a decade, machine learning followed empirical scaling laws. Increasing compute and dataset size predictably improved performance. Researchers estimate that high-quality human-written text on the public internet will be fully exhausted before 1928. Real-world data collection faces three fundamental barriers: high financial cost, severe privacy regulations, and extreme scarcity of rare events. Traditional data pipelines suffer from human annotation errors, bias, and impossible scaling costs. Synthetic data artificially generates high-fidelity labels, perfectly structured samples, and infinite training volume at near zero marginal cost. Consider human labeling throughput versus synthetic generation speed. Algorithms generate millions of labeled images in seconds. Furthermore, synthetic engine labels are free from human subjective error, providing perfect ground truth coordinates and segmentation masks. Synthetic data is not a temporary patch. It is becoming the primary foundation of future artificial intelligence models. Chapter 2. Class Imbalance and Classical Machine Learning. Consider fraud detection in banking. Out of 100,000 transactions, 99,900 are legitimate, and only 100 are fraudulent. If a machine learning model simply predicts every transaction is legitimate, it achieves 99.9% accuracy while failing completely. The confusion matrix reveals the truth. Zero true positives means the model is useless in production. In feature space, the decision boundary gets overwhelmed by the majority class, smothering minority data points. Simple duplication overfits, whereas synthetic oversampling interpolates brand new synthetic feature points. Enter SMOTE, the synthetic minority oversampling technique. It operates by identifying k-nearest neighbors in feature space. SMOTE selects a random neighbor along the feature segment and interpolates a new synthetic data point between them. Mathematically, the synthetic point x new equals xi plus a random uniform multiplier lambda times the vector difference. Advanced variations like Addison generate more synthetic samples near difficult decision boundaries where classification density is low. Classical tabular synthetic algorithms solve imbalance across finance, medical diagnosis, and cybersecurity. By balancing the class distributions synthetically, models achieve optimal precision recall trade-offs without losing critical minority signals. In medical disease diagnosis, rare conditions affect less than 0.01% of patients. Synthetic data allows life-saving detectors to train. In cybersecurity, novel zero-day network attacks leave no historical trace. Synthetic attack generators simulate threats before hackers strike. Without synthetic balancing, machine learning models remain completely blind to rare, high-impact events. Chapter 3. Deep Learning, Computer Vision, and Privacy. Deep neural networks require millions of high-resolution images to learn visual representations. Generative adversarial networks revolutionized image synthesis by setting two neural networks in competition. The generator creates fake images from random noise vector Z, while the discriminator attempts to distinguish real from fake. Mathematically, GN training is formulated as a minimax game with value function V of D and G. Medical scans contain sensitive patient identity. Synthetic GN scans preserve pathology features while removing personal identity entirely. Global privacy legislation like HIPAA in the United States and GDPR in Europe prevent open sharing of medical datasets. Differential privacy mathematically guarantees that individual training records cannot be reconstructed from synthetic generator weights. Now consider autonomous driving. A self-driving car cannot safely wait to encounter a dangerous crash in the real world to learn to avoid it. Driving scenarios follow a long-tail distribution. 99% of miles driven are mundane highway driving. 3D simulators allow autonomous vehicle engines to drive millions of extreme collision scenarios safely inside synthetic physics environments. Platforms like NVIDIA Omniverse and Carla render photorealistic weather, lighting, and sensor LiDAR outputs. A major challenge in synthetic vision is the sim-to-real domain gap. Models trained on synthetic render engines can fail on real photos. To solve domain gap, domain randomization randomly alters textures, lighting, and camera noise, forcing models to learn domain invariant features. Beyond GNs, diffusion models now generate ultra-photorealistic computer vision datasets with detailed natural text prompts. Forward diffusion progressively adds Gaussian noise to an image until pure noise remains. Reverse diffusion learns to step-by-step remove noise. Score-based generative modeling estimates the score function, guiding noisy states toward high-probability data manifolds. Generative diffusion models accelerate computer vision dataset creation by over 100 times. Along with RGB images, synthetic generative diffusion outputs pixel-perfect depth maps, surface normals, and segmentation masks simultaneously. Modern deep computer vision pipelines rely heavily on generative adversarial networks, diffusion engines, and physics simulators. Chapter 4: Large Language Models, Reasoning, and Self-Play. Pre-training frontier large language models requires trillions of high-quality text tokens. Raw web-scraped text is filled with spam, toxic content, and low-quality social media comments. To solve this, researchers introduced the Self-Instruct framework, allowing language models to generate their own instructional datasets. Starting with a tiny set of seed human instructions, the teacher language model generates thousands of diverse instructions and answers. Training small models on raw internet text yields poor reasoning. Training on synthetic textbooks yields high intelligence in lightweight models. In constitutional AI, language models critique and refine their own answers according to a written constitution of principles. For mathematical reasoning, models generate multiple solution paths and filter outputs using rejection sampling. By pairing language models with Python execution environments, code outputs are automatically verified by unit test passes. The self-taught reasoner, or STAR algorithm, fine-tunes language models iteratively on rationales that led to correct final answers. Self-play reinforcement learning, pioneered by AlphaZero in chess and Go, generates synthetic gameplay sequences without human domain knowledge. AlphaZero achieved superhuman chess mastery purely through self-play synthetic game data generation. Model distillation uses a giant teacher model to generate synthetic step-by-step outputs that train compact student models. The distillation loss minimizes the Kullback-Leibler divergence between teacher probabilities and student output distributions. Unfiltered synthetic data risks model collapse. Recursive training on low-quality synthetic outputs causes variance decay. When Generation N model trains on Generation N-1 synthetic text without filtering, the distribution tails disappear completely. Variance loss accumulation causes the recursive model to lose creativity and repeat narrow boilerplate sentences. To prevent model collapse, synthetic data generation pipelines enforce rigorous automated filtering, deduplication, and reward verifiers. When combined with programmatic ground truth verification, synthetic language data unlock frontier reasoning benchmarks. Synthetic text generation has transformed language model instruction tuning, code verification, and reasoning distillation. Chapter 5: The Future of Data Engineering and Synthesis. Future AI development will replace passive web scraping with active synthetic data engines. Automated reward models evaluate synthetic text quality, scoring logical consistency, grammar, and factual grounding. Semantic deduplication algorithms cluster synthetic embeddings to eliminate repetitive sentence structures. Gartner predicts that 90% of data used in machine learning models will be synthetically generated by 1930. Data engineering is evolving from passive data gathering to active data compiler design. Human roles are shifting from manual labelers to data architects who design verification rules and audit synthetic outputs. The traditional data pipeline was slow and bounded by human limits. The synthetic engine is fast, private, and unlimited. In summary, Pillar 1 solves data scarcity and class imbalance through algorithmic oversampling techniques like SMOTE. Pillar 2 unlocks computer vision, robotics simulation, and privacy-safe healthcare training using GANs and diffusion engines. Pillar 3 scales large language model reasoning through self-instruction, rejection sampling, and self-play reinforcement learning. Synthetic data is the bridge between human-level intelligence and superintelligence. Thank you for watching Simple C. Subscribe for more in-depth mathematical and artificial intelligence visual guides.